some problems yesterday's presentation to hopefully clear up some of the issues we had about, or one problem to clear up the issues we had about waves. But I want to give you a chance to ask, because if you weren't here on Monday, I kind of had to do an about face and think on my feet in the middle of the class, because I figured out that we didn't have a lot of the terminology we needed to have to talk about waves. So I had to go back. It was probably very disjointed and confusing. My apologies if you had to sit through that. But I hadn't planned on doing that, so I had to switch gears. So let me just ask first, are there any questions about terminology of waves? When we say things like frequencies or wave numbers, do we know what those are? Do we have residual questions left over from that? Amplitudes, whatever. They tell me I'm supposed to sit here in the uncomfortable silence, so somebody probably has a question. My tendency is to go fast, so I want to give you a chance to ask the questions. It's really uncomfortable. Okay, fine. If you don't have questions, that's fine. If you do, please ask them. Just you can interrupt me or whatever. Are there any questions about how to read off information from the solutions to the wave equation? When we talk about the equation describing a wave as some sort of a cosine omega t minus or kx minus omega t, any of that stuff that you have questions about? Okay. Okay.
I'm still having trouble understanding directional stuff with it.
Okay, so you're talking about for electromagnetic waves specifically. Alright, perfect. What I should say is an electromagnetic wave made? What two things come together to produce an electromagnetic wave?
Electricity and magnetism.
You said electricity and magnetism. You're not wrong, but let's sharpen that. What about electricity and magnetism? What specifically? Oscillating what? Fields. There we go. Yeah, so electric fields and magnetic fields are contained, oscillating magnetic and electric fields are contained in electromagnetic radiation or electromagnetic wave or light. I'm saying the exact same thing just with different words, right? So the E field oscillates in one dimension. Let's imagine that I'm looking at a wave coming straight at you, right? So I'm going to draw a wave coming out of the board. The E field might be oscillating in this direction. If that's the case, the B field is then oscillating in this direction, such that these two are perpendicular. That's a hallmark, and you can take it to the bank. In every electromagnetic wave, the E field and B fields are oriented perpendicularly or orthogonal or normal, whatever your preferred nomenclature is, to each other. Right? They're always perpendicular. I've drawn the B field much smaller than the E field. That is usually how it works out. In fact, that's pretty much how it works out all the time. And that will come important later when we talk about polarization. But what's happening is the E field is oscillating. Right? At some point, I can't draw it in 3 dimensions, but if you were to flip your perspective, the E field would look like this, right? Where when I say it's oscillating, that means it's oscillating in magnitude and direction. But when you look at it, what I'm saying is at this point it's pointed upwards, which is why I have this. This point is pointed downwards, which I have this, right? So the E field is oscillating, and the B field is doing the same thing. And they're always oriented in this direction. Or, sorry, not in this direction, in this relationship, perpendicular to each other. They're also, both of them, we say mutually perpendicular to the propagation direction. So the wave is coming out of the board, right? There's another right angle. The propagation direction is normal to the plane of this board. These are oscillating in the plane, so we can't get away from 3 dimensions, and everything has to be mutually perpendicular. What that means is a convenient way to characterize those is to use your good old 3-dimensional axis, x, y, and z, right? So, and it doesn't matter what you call them, right? It doesn't matter what you assign to be what variable. If you say that the E field is oscillating in the y direction, which is how we would standardly write the y direction, right? That means the B field, or if you say that the B field is oscillating in the x direction, propagation direction is then z. It doesn't matter what you call them. You can call this x and this y, this would still be z. You call this Z and this X, and this would be Y. It's the other one. When you write out that equation, the solution to the wave equation, what we should really say, is that the electric field as a function of space and time. Why space and time? Well, it's a function of time because it's oscillating in time. Like it's just getting bigger and getting smaller. That's time dependence. But it's also a function of position because this thing is propagating through space. And wherever you look on that wave, it's going to have a different value. So you've got to specify, I'm looking at this point, at this time, and that's the value of the field there. If I wait another second, it's going to change. Or if I look somewhere else, it's going to change. But if you want to talk about the value of the field, because it's oscillating and propagating, I've got to say, at this particular location, at this instance in time, what is the value of this field? That's why we have two variables here. It's a multivariable function. So E is, the propagation direction is actually contained right here. If it's propagating along the x direction, that's where you're looking. At 1 meter, at 2 meters, that's where I want to know. So the propagation direction is right here. The oscillation direction, usually, you don't have to have it in there, but usually it would be subscripted here. So maybe this is y, right? That works over here. Yeah, let me change this to match up with what I'm drawing. Call this z, right? We'll call that the z direction. That means we're propagating the x, right? Sorry, I didn't match that up. But the y direction here says that's the oscillation direction. It's right here, oscillating up and down. And that's going to be the amplitude, which is the max value of the E field. We usually indicate that with an E naught. And then the trig function cosine omega, kx minus omega t. The spatial frequency, right? How many of these cycles fit inside a meter? That's the spatial frequency, sometimes called the wave number. In fact, always called the wave number. I just like spatial frequency because that tells you what it is, right? The spatial frequency or the wave number. This is the temporal frequency. It's an angular frequency, but it's how many of these things fit inside 1 second. How many cycles fit inside 1 meter is the wave number. How many of these things fit inside 1 second is the temporal frequency, right? It depends on what you're using to measure. If you're using a meter stick, that's wave number. If you're using your stopwatch, that's omega. Okay? So, knowing this, you can now just write down the B field, or most of it. B. What's the oscillation direction of B? Z, right? Do you need this diagram to know that at this point? You don't. The propagation direction is here. Orientation of the E field is here. The B has to be in the other one, right? The only one left is Z, so that's here. B is oscillating in the Z direction. That's going to equal amplitude, max value, cosine. What about the argument of the trig function? Same. Why? Justify that. What is it about these two waves? Because these are two different waves. But that's not true. These are two, well, it's one electromagnetic wave. But I'm graphing it. I'm representing it as two different wave functions. The cosine is the wave function here, right? What enables me to just write this down? Kx minus omega t. Why is it the same? They're in phase. When the B field's at a maximum, the E field's at a maximum. When the B field is at a minimum, the E field is at a minimum. What that means is that the wavelength, the frequency, the wave number, the angular frequency, all this stuff is exactly the same. Now, amplitude will not be the same, not even the same units, right? This is volts per meter, this is Tesla. The argument of the trig function is the same because the waves are in phase. When E has reached its amplitude, B has reached its amplitude, right? They both come back down to 0 and then they go the other way, right? 0, maximum, 0, maximum, 0, so on and so forth. Does that make some sense? All right, good questions. Other questions about this? Again, there's a lot of talking to these problems. I don't think that the work we do with them is that intense. You just have to know how to read it off. But if you don't know how to read it off, it's hard. So now's the time to ask your questions. Yeah?
How can you express E naught in terms of E naught? Let's
Yeah. So past this, we have a couple of other relationships that we need to talk about. The first one is your wave speed. Now, this is true for any wave. The wavelength, which has units of meters, times the frequency, which has units of 1/seconds, gives you units of meters per second. That's a speed no matter how you slice it. So this expression, lambda f, is equal to the wave speed. For electromagnetic waves, instead of writing a v, we write a c for the speed of light. There is another way to calculate this, and I never get it right. I get the denominator and numerator mixed up if I don't check. If I'm not standing in front of a classroom, I can tell you exactly what it is. But as soon as I'm not standing in front of a classroom, or as soon as I am, here we are, right? No, I'm not going to find out. Somebody has it's either E over B or P over E. Yeah, okay, thank you. That's what I was leaning to. The value of the electric field divided by the value of the B field. And this is just E over B, right? At any time. The reason we don't typically like to use that is because both of these fields go to 0 at lots of points, right? I erased my graph. It goes to 0 here, which is a problem, right, for the numerator. The denominator, not a problem for the numerator. So we typically just pick out the one point where they're at a maximum and say that. So this is a relationship that you just, it's on your formula sheet, you don't have to memorize it. But this should always be in your back pocket. The left part of this is the wave speed equation, true for any wave. The right side is true for electromagnetic waves. It makes your life a lot easier if you know where to find these. That's a good question. And there's some algebra to be done to show that you can do that. I'm not gonna, it's not that hard. I'll put up some equations in a second which will lead you to it if you so desire to do it, but that's the end result. Questions about that? Other questions? All right. After we talked about that, we talked about the idea of energy density and why that is important in a wave, right? A wave carries energy. If you've ever been at the beach and got hit by a large wave, you understand that they carry energy, right? That's what a wave is. A wave is a propagation of energy without a net propagation of matter, right? You can move energy around all day long by moving matter around. You did it when you ate breakfast this morning, or last time you filled up your gas tank. You're moving energy, but you're also moving matter. A wave moves energy without a net transfer of matter, right? Waves, water waves move matter around. Sound waves move matter around. There's no net transfer. The elements of the medium are oscillating, right? The air molecules between my vocal cords and your eardrums are going back and forth, back and forth, back and forth, back and forth. If you've ever been fishing on a windy day, you understand what I mean? When a wave goes across the surface of the pond, your float just goes up and down. That's what the water's doing. If it moves, that's because of the wind, not the wave. The ocean's a little different at the beach because the waves are breaking and things get all cattywampus. But out in the deep ocean, before the waves break, they don't move you, they move you up and down, but there's no net transfer. So that's what a wave is. It carries energy, but doesn't transfer matter. In the case of electromagnetic waves, there's no matter to carry anyway, right? They don't require matter for a medium. But if you've ever got a sunburn, you know that they carry energy, right? That's the deal. So we talked about the energy content of waves, but that's really difficult to talk about because waves are spread out. Right? How much energy does this wave have? Well, how big is the wave? That's not always an easy question to answer. But energy density is the right way to go about it. The energy per unit volume. We talked about that and how to express that in terms of, we talked about how to express the energy density in in terms of these variables we've been talking about. And that's it somewhere. Maybe not. I've lost one. Yep. Lowercase u for electricity, 1/2 epsilon naught E naught squared, right? I'm putting the naught there, it doesn't have to be there, but this is the maximum value, right? At any given time, I can just cover up the naught, because at any given time, it's the E field at that time. So if you're talking about the maximum value, that will be your maximum value of the E field there. And then U be 1/2 E naught squared over mu naught, right? So this is an energy density. This is a joule per cubic meter. What else might those units give us? Anybody know? You might not know this, and it's understandable if you don't. Okay, let me just back up. What if, what's the best way to do this? I'm not used to starting from this side. That's okay, I'll start from the other side. Just throw that anywhere. Force per unit area, what's that? Pressure, yeah. Units of pressure is a Pascal, right, or atmosphere, or a torr, depending on your application. But a Pascal is the SI standard. That is a Newton per square meter, right? Newton per square meter. What happens when you multiply anything by 1? Do you change it? No, you don't. That's quantities or units. So let me multiply this by 1. Meter over meter. I didn't change anything, right? What do I get here? Well, in the denominator, I get a cubic meter. What do I get in the numerator? What's a Newton times a meter? Say what? Work. But what are the units of work? Joules. Right? Which is what I said this was. A joule per cubic meter. If you've never thought about pressure that way, you should start thinking about pressure that way. Pressure is defined as a force per unit area, but the more fundamental way to think about it is an energy content, energy per unit volume. So this energy density we've been talking about leads actually directly to the idea of pressure. And this wasn't lost on Maxwell when he was figuring all this stuff out. So what would that even mean for the energy content of an electromagnetic wave to exert pressure? What does that even mean? Well, Maxwell theorized that actually that would be the case. That if light is incident upon a surface, not only is it delivering energy, which it is, that's why we get sunburns, it's actually causing or exerting a pressure, a force per unit area. And he was right, it actually does. You can see this experimentally. We don't really experience it in our everyday life because the pressure is very small compared to the energy delivery. So you walk out in the sunshine and it feels warm, right? You don't feel pushed back like you expect from a pressure. But there is pressure there. There is what's called a radiation pressure. And if you have really sensitive equipment, you can actually measure it. What they did was they hung 2 mirrors from a little filament inside a vacuum glass jar, and they shone a light at one mirror, and the whole apparatus tilted. I'm exaggerating, it doesn't tilt that much, right? It deflected because light was incident upon this mirror, and the whole thing went whoop, right? Because there was a pressure exerted there. So this is really interesting, right? The idea that light exerts pressure on things. We don't notice it in the atmosphere here, but if you go into a vacuum, it actually is noticeable. And they have to calculate that, take this into account when you're projecting satellite trajectories in orbit, right? Because the radiation pressure from the sun can actually knock them out of the orbit they're supposed to have. The idea of a solar sail has gained popularity in the past few decades. The idea that you could put a ship in space and just erect a big silver sheet and the sun will actually push it. That's a thing, and it can actually happen. People haven't utilized that yet in a practical way, but it's a possibility, and they do have to take this into account with any sort of satellites, because the satellites get pushed around a little bit by the sun. To see how this works, let's try to relate a couple things. So the last piece of review before we put all this together. This is the last thing we saw. Where I here is the intensity of an electromagnetic wave. Right? We talked about for light, that would be like the brightness. The intensity of a sound wave would be like the volume. Right? So in this case, we're talking about electromagnetic radiation. If it's visible light, we'd say brightness. If it's not visible, that doesn't make any sense. Right? But it's something analogous to that. Right? You can't say that infrared radiation is bright because we can't see it. But there's something analogous to that going on. Okay? So this thing, the pointing vector, which is, we never really use this. I mean, you should know what this is. In future classes, you might use it. In this class, we're not going to use this explicit form of it, but this is what it is, right? And notice, this is the E field and the B field of this particular wave. So you can form the pointing vector. The pointing vector also will give you the propagation direction, because remember the cross product has to be mutually perpendicular to the two vectors that you're multiplying. But the pointing vector changes in magnitude constantly, because E and B change in magnitude constantly. Our solution to that in physics is always to take an average, so the time average pointing vector turns out to be the intensity of the wave. So the intensity of the wave and the time average value of the pointing vector calculable with any of these equations, right? This is it in terms of the E field. This is it in terms of the B field. This is it in terms of both of them in the magnetic constant. You can formulate it in terms of the epsilon naught if you want to. But any one of these, just depending on what you have, will give you the intensity of the wave or the time average value of the pointing vector. All right. So you might recognize this, or you would recognize it if I hadn't erased the equations. You might recognize this as C from here times the energy density associated with the electric field. Right. 1/2 epsilon naught E naught squared was what I just gave you as the energy density of the electric field. Okay, fair enough. What that means is that I can express the energy density as I over C. The intensity is divided by the speed of light. Okay, this is what we're getting at. This is the energy density, but also expresses the radiation pressure. This is what tells you how much pressure is exerted on a surface just by shining a light on it. Again, not something you're ever going to notice in the real world, but in an experiment or out in space, this can happen. Or it happens all the time. It can have a noticeable effect. So the energy density turns out to be just the intensity divided by the speed of light. All right, how do we put all this together? Well, later, after we get finished with this chapter today, we're going to talk about other qualities of light that we know and love, like reflection, right? You got ready looking in a mirror this morning. That's a property of light that you understand. Reflection. But not everything reflects, right? So I want us to imagine a wave of light, and I'm going to draw it as a vector. We call it a ray of light. It's just an approximation, but you can see what's going on here. There's a ray of light, which is a wave, but I'm calling it a ray, coming in over here, and it's going to strike an object. This object, we're going to assume, reflects every single bit of that light backwards. Right? This is pretty much what happens in your bathroom mirror. It reflects every bit of that light backwards. And so the light comes in, and then it leaves. But there are other materials which don't reflect light, right? Everything reflects light, or most things reflect light somewhat, right? My shirt reflects light somewhat. That's how you're seeing it right now. Light is bouncing off my shirt and getting to your eyes. But you can't see yourself in my shirt like you can see yourself in a mirror. That doesn't make any sense. So my shirt is only partially reflective. It's actually absorbing, and right, if you've ever worked outside in the summer in a black t-shirt, you understand that absorbs the energy. A white t-shirt's going to reflect some of it, right? You're still going to get hot in Alabama, but it might be able to bring you a little comfort to wear a white t-shirt as opposed to a black t-shirt if you're working outside in the summer. Because the white reflects more of the light than the black does. It So absorption and reflection is on a spectrum.